warahmatullahi wabarakatuh. First of all, I'd like to introduce myself. My name is Bob S. Effendi. I'm the Chief Operating Officer of PT ThorCon Power Indonesia. A little bit on PT ThorCon Power Indonesia. ThorCon Groups has been in Indonesia for the past 5 years, since 2015, in promoting the thorium molten salt reactor to develop and build the thorium molten salt reactor 500 since 2015. And before, we were operating under the auspice, under the umbrella of a representative office for the past till 2021. But then in 2020, we have recommendation from the government, and part of the recommendation of the government that they need to do several studies, and in order to do these studies, we were asked to change into a PT company. So we become a PT company in August 2021. Currently, we have 15 employees, and some of them are interns, and 3 of the interns we have is already ITB graduates. So so we are progressing, and with this proposal with the government, and hopefully within very soon that we will propose to the government, and the government will consider. So hopefully 2023, hopefully, of course, still hopefully, because you know how nuclear is in Indonesia, but hopefully in 2023, this could become a national project. Having said that, then I would like to give my gratitude and appreciation, especially to ITB, and big thanks to the Ibu Rector, Bu Reni, who's been supporting from the beginning that we have signed the MOU, and also the Dean of the Dean, and for having this opportunity, and special thanks also to Chairman of LPPM, Pak Yuli, and a very, very special thanks to Pak Rino that has been facilitating all this activity, and we are now about to sign the agreement to build the fuel lab in Jatinangor, which hopefully by early next year should be operating. Now, without further ado, I would like to introduce our speaker, which is Professor Kun Chen. He is a ThorCon Group's nuclear chief officers, and he is probably the most prominent nuclear expert in the world for molten salt reactor, because not only that he was involved in designing what's currently to be the first molten salt reactor would be operating in China, which is under SINAP, which is 2 megawatts. So he was involved in the design, then in the licensing process. And so then he moved to Moltex in Canada, was also a molten salt reactor technology. He involved also in the licensing process. So Dr. Kun experience is very quite extensive, and I think would be beneficial. His vast knowledge in molten salt technology, I think the only person in the world, I think, that have a vast knowledge of molten salt technology from different technology, including now ThorCon. So he works basically now already on 3 different technology, Synapse, Moltex, and now ThorCon Power. So I think without further ado, I would like to introduce our speaker. Not yet, yeah. Sorry, not yet. Don't worry, everybody. Hold your horses. Right? Of course, we have still several keynote speech talking. So again, I would like to end my speech. I think everybody is waiting to hear your speech, Kun. So we have already, I see here 42 people waiting on the Zoom. Hopefully it will be more, but don't worry, it'll also stream to YouTube. So we don't know on the YouTube how many people are watching here. So I don't like to talk very much. So I think again and again, I'd like my greatest appreciation to Institute Teknologi Bandung for having us and cooperating on developing the molten salt technology, and also special thanks to Pak Rino, Pak Imam, Pak Hardev, and Pak Fainan in facilitating all this cooperation that we are having with ITB. Thank you very much, and thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Well, thank you, Mr. Board, for the opening remarks as a representative from ThorCon. Now we will move to the opening remarks from the chairman of LPPM ITB, Dr. Yuli Setio Indarto. Dr. Yuli, please, for the time and place.
Terima kasih Pak Asril. Bismillah, Assalamualaikum warahmatullahi wabarakatuh. Distinguished ladies and gentlemen, Dean of Faculty of Mathematics and Natural Sciences, Professor Wahyu Sri Kutomo, Mr. Prof. FGD from PT ThorCon Power Indonesia, of course, Professor Dr. Kun Chen, the leading expert in the nuclear technology of ThorCon Group, and also the head and college from the postgraduate program of Nuclear Engineering of Faculty of Mathematics and Natural Sciences ITB, Pak Siddiq Permana and college. Distinguished ladies and gentlemen, welcome to Bandung, mainly for Pak Kun Chen and Pak Bob. Today we have a special guest lecture from Professor Kun Chen. We know that he currently has a position as a Chief Nuclear Officer at ThorCon Group. His expertise is within the nuclear technology. We know that he has experience as a nuclear engineer at Argonne National Laboratory, USA, and also Director of Shanghai Institute of Applied Physics, Academy of Sciences, China. ITB and PT ThorCon Power Indonesia will start a collaboration, as well as to collaborate with leading experts from the prestigious university, from the California, Berkeley, and Virginia Tech. This collaboration involves research and development of nuclear sciences and technology, especially in molten salt reactor technology. The technology certainly supports the demands of energy mix to reduce the greenhouse gas emission as the objective of all countries in the world, including Indonesia. Indonesia has a plan to have a net zero carbon emission in 2060. That's why energy mix is important to reach the objective. ITB supports the development of new and renewable energy, including nuclear technology, of course, as it has been listed by the government as one of the priorities in research and innovation. In ITB, we have several research centers that deals with the energy sectors. For example, the Research Center for New and Renewable Energy, Center for Energy Policy, Center for Catalysis and Reaction Engineering, and so on. That's why we welcome all kinds of contribution to support the research center. We hope in the future we can collaborate closely to support the new and renewable energy technology in Indonesia. We hope that this collaboration will also give opportunity to develop our education, particularly for the graduate program in multidisciplinary studies. Programs such as joint supervision between two universities, visiting professors, staff exchange, and student exchange. ITB and of course Indonesia are expecting that such technology would be beneficial to realize our nation hope in fulfilling the sovereignty of national energy. I believe that one kind of new or renewable energy is not enough to fulfill the national energy consumption. So the mix of energy, mix of new and renewable energy is important to fulfill our objective for the carbon neutral in 2060. Nuclear technology is one of the new energy. The technological innovation based on scientific merit is the key factor to finding success in this mutual collaboration. Thank you for your participation. Thank you again for Professor Kun Chen and Pak Bob. We wish you had a fruitful discussion in the seminar today. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Yuli, as chairman of LPPM ITB. Now we will move to the Dean at Faculty of Mathematics and Natural Sciences, ITB, Professor Wahyu Srigutomo. Professor Wahyu, please, your time is yours.
Thank you, Pak Asril. Assalamualaikum warahmatullahi wabarakatuh. ITB Vice Rector for Research and Innovation, Professor I. Gdewenten, Chair of Institute for Research and Community Service of ITB, Dr. Yuli S. Indartono, Head of Postgraduate Program of Nuclear Engineering at Faculty of Mathematics and Natural Sciences, ITB, Dr. Sidik Permana, Mr. Bob Effendi, CEO of ThorCon Power Indonesia, all distinguished guests, colleagues, ladies and gentlemen. It is a great pleasure to us to have Professor Dr. Kun Chen today participating in FGD series, Volume 7. Please accept my apology. Today, I cannot physically join Professor Kun Chen at ITB because I currently in Surabaya attending a workshop on accreditation process of academic institution. Today, we will have a lecture by Professor Kun Chen. He currently has a position as Chief Nuclear Officer at ThorCon Group and has expertise in nuclear technology. He will deliver a talk on introduction to molten salt reactor technology, and known as the fourth generation of nuclear reactor development in the world. Professor Chen has been at Argonne National Laboratory, USA, and Shanghai Institute of Applied Physics, Academy of Science, China. And as we all know, as we have known, ThorCon and ITB has signed a memorandum of understanding for the collaboration in the field of molten salt reactor development. This collaboration involves research and innovation that may support particularly the demands of energy for the future of Indonesia. Our faculty at ITB has established postgraduate program in nuclear engineering. So we hope that we could establish a collaboration in terms of education, research, and innovation with the ThorCon, as also said by our head of LPPM, and other prestigious worldwide universities in the future. We have that we can learn and we can hear more on molten salt reactor technology today from Professor Chen, and we wish everyone have a fruitful discussion in the seminar today. Thank you very much. Please enjoy this FGD. Wassalamualaikum warahmatullahi wabarakatuh. Thank you all.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dean of at Faculty of Mathematics and Natural Sciences, Professor Wahyu Sri Gutomo. Now we are going to continue our FGD series of, from LPPM to the keynote speech. And it's from Professor Dr. Kun Chen. Right now, as has been introduced before, please, Professor. He is a ThorCon Chief Nuclear Officer, and the proposed title is Introduction to Molten Salt Reactor Technology. And talking about today's topic, there are many types of reactors, as we know, just like cars, but not as many as type of cars, of course. Even we have like several generations for reactors. We have at least 4 generations, generation 1, 2, 3, and 4, and each generation improved the previous generations. And MSR is one of the type of reactors that belongs to generation 4. And also we, in our group at ITB, we also have several researchers that working in terms of generation 4 reactors. Also regarding the MSR, there are researchers that working for the neutronics. Usually when we are talking about reactor, maybe we will listen about the neutronic, and also about thermal hydraulics, and also about materials. And right now we will have much more knowledge from Professor Dr. Kun regarding the MSR. So Professor, please, time is yours.
Thank you very much. Can everybody hear me?
Yes. Yeah.
Okay. Thank you for the introduction. Thank you, Professor Asril, for the introduction. So I'm extremely happy to be here, to be in the beautiful city of Bandung, and the famous University of ITB. I've been here the story of ITB for a long time. I was able to having Zoom meetings with faculty members and students from the university. Finally, I get the chance to visit the university and giving the presentation. And hopefully, I will be able to bring some new information and the topics for discussion to the faculties and students here. So today, the title of my presentation is about an introduction to molten salt reactor. And also I'm going to spend some time to introduce you ThorCon Indonesia. So let me start the presentation. Maybe I should wait. Okay. All right, so the first question, of course, would be, what is MSR? Many people knew MSR, but yet a lot of people did not have exposure to MSR. So the International Atomic Energy Agency recently published a technical document about the status of molten salt reactor technology. In that document, there's a definition of MSR. And as you can see, there's a variety of types of MSR. As you, Professor Asril, as you mentioned, there's many types of cars, and we also have many types of MSRs. And MSR is one of the 6 generation 4 nuclear reactors. And the generation 4 will use fuel more efficiently, and will reduce waste production, and will be more economically competitive. So that's the conclusion from the Generation 4 International Forum. So let me start with a little bit history about MSR. the early days. So the first MSR was invented by the Oak Ridge National Laboratory in the United States back in 1949. As you can see, the reactor initially was designed to be used in the airplane. The first one, of course, is a very preliminary one. It operated only for 100 hours. So that's where the legend started, but it didn't end there. There's a long history of MSR development. So the second one is the most famous one within the nuclear community, which is Msre, the molten salt reactor experiment. It's also in Oak Ridge National Laboratory. It reached the initial criticality in 1965 and operated at the thermal power close to 8 megawatts until 1969. So in that experiment, different type of fuel were tested in the reactor, including uranium-235, uranium-233, and plutonium-239. So it shows the MSR is a versatile reactor that allows you to use a different type of fuel. Now, MSRE in Oak Ridge was also part of the thorium uranium fuel cycle development. So that's why uranium-233 was used. So on the right of the screen, you can see a top view of MSRE. Okay, so the MSR technology started in the United States, but it spread around the world. Here is the activities, historic activities in the countries in the alphabetical order. As you can see, countries such as China, France, Germany, Japan, Netherlands, Russia, Switzerland, and United Kingdom, they all had or have MSR programs. So as we discussed, there's so many types of MSRs. Now you consider, so you can categorize those reactors into multiple classes, categories, and you can consider the fuel they're using. Some of them are using uranium, some of them are using plutonium, some of them are using thorium. And of course, it can be a thermal reactor, or it can be a fast reactor, and it can be a burner, it can be a breeder, and it can also be a converter. And as for the sort, we're talking about molten salt, but there's a multiple type of sorts. At least you can have a fluoride sort as the original MSRE we're using, and also you can have a chloride sort. You can also have other type of sort. And for the core, you have single fluid, two fluids, and several other types there. And for the side, you can also have land-based, non-land-based. So as we can see, it's a very versatile type of technology. It can be used under different situations for different applications in different countries. So just some examples of the MSR around the world. So from top left, we can start. The first one is the what we call a molten salt cooled reactor. So the concept was actually proposed by Oak Ridge National Laboratory itself. In that type, the fuel is solid fuel, mainly in many cases are triso particle fuel, and the coolant of reactor is molten salt. On the top in the middle, it's a Fuji reactor proposed by Japanese researchers. And on the top row on the right, it's what people call stable salt reactors proposed by Motex Energy. And at the bottom, on the left, it's a French design. It's a fast reactor. In the middle, it's a Russian design. They call it the Msr, which is the waste burner. And on the bottom row on the right, it's a Chinese concept proposed by Shanghai Institute of Applied Physics, Chinese Academy of Sciences. So it's a molten salt design that is currently being built in China. And this is just an incomplete list of MSRs. There's much more which you can find detailed information from the recently published IEA report. The benefit of MSR. So why we're developing so many types of MSRs? Because there's tremendous benefit from the MSR technology. First of all, it enhances safety. MSR tends to have a passive safety features. It has a system that operating in atmospheric pressure. And molten salt tends to bind the radioactive isotopes and dissolve it into the salt. So many safety features, and the MSR vendors were able to take advantage of those safety features from molten salt and come up with advanced design that has enhanced safety. And a second point is the flexible fuel. As I said in the previous slides, you can use thorium, you can use plutonium, and you can use uranium in that in molten salt. So good for different countries. Some countries has more thorium. They tend to use thorium, and some country wants to burn plutonium. They can do that as well. The third point is the improved economics. So because you have a versatile fuel, you have enhanced safety. So it also have implication in the economics, which I will cover that in detail when we introduce ThorCon Indonesia. So the fourth, the last one, but not the list, is the point that MSR, as the same as other nuclear energy, it provide clean and dispatchable energy. So you could turn it on and turn it off as you wish. I just want to use these slides to quickly review the safety features of molten salt. The molten salt enables the low pressure design, mainly because the salt has a very high boiling point, usually above 1400 degrees C. So you don't have to pressurize the system. So you can have a low pressure design, which reduce your risk of release, and also reduce the cost of the components. And then you have a large temperature margin. And because typically the reactor will operate at around 600, 700, 800. The boiling point, on the other hand, is up to 1400. So you have a large temperature margin. And then you also have a large thermal capacity. So the molten salt has a similar thermal capacity as water. And so that means when you have an accident, the accident will progress very slow. So you have ample time to react. And the molten salt does not react violently with either air or water. So even you expose the molten salt to the environment, it won't react violently. And also it forms stable compounds with radioactive elements. So the radioactive elements will become fluoride or chloride, and it will be dissolved in the salt and basically stay there. So there's less chance for them to be released to the environment. And the molten salt is chemically stable when irradiated. So after being irradiated for years or maybe decades, the molten salt are still stable. They're not generating gases, generating other type of chemicals. Because it's liquid, we can also do fuel loading and fuel unloading online. So that means you can have a less excessive reactivity when you first load the fuel. And you can just add a fuel on the line. And it also enables the online gas removal. If you have a, let's say, a fuel, nuclear fuel in the cladding, you have to worry about the internal pressure increasing over the time, because the noble gases, the xenon, krypton, will be generated over the time, and the cladding will be pressurized. And for our case, the liquid fuel will enable you to remove the gas online, so you won't have a accumulation of radioactive noble gases in your system. So it decreases the pressure and also decrease the amount of radioactivity you can release. So a lot of safety features. I cannot go over every single one of them. And but again, I encourage you to read. There's a lot of molten salt publications. They're addressing and each single safety features. Okay, so I guess I talked quite some time about the molten salt technology. I guess the next natural question is, can Indonesia have MSR? The answer is yes. So I'd like to introduce you the ThorCon Indonesia team. So ThorCon Indonesia is a private company. We're a developer and future operator of MSR power plant in Indonesia, supplying clean, safe, and dispatchable electricity cheaper than coal. And we have a vibrant Jakarta-based team led by industrial expert, as you can see on the pictures. In the middle is Bob. You all know him. He's the leader of the company. And we have, he's surrounded by young talents and experts. So it's a very vibrant team. As you can see, many female team members. They were very active. And also I want to point out there's former ITB students in that team. So we're very excited to have the office in Jakarta to try to develop the first ever nuclear power plant in Indonesia. So what we do, this is the ThorCon nuclear power plant. It's a 1 gigawatt design. As you can see, it consists of 2 units, each have 500 megawatt. And in the middle, there's a ship, we call it can ship. It's transporting the nuclear fuel and components during the operation. Now, this is a overview of the power plant. It's really like a ship. It is designed and will be built as a ship. To the right, it's the used fuel storage, and then you can see there's 4 ponds there, which we store water for cooling. And to the left, there's a full round circular shaped cylinders. Those are the reactor core, and we call it cans. So we have 4 of them, and at any time, only 2 of them are in full power. The other 2 are in cool down modes. So, and then after that, to the left, you can see there's a different type of molten salt loops. Eventually, there's steam generator, and then the most part on the left is actually the conventional steam turbine generator systems. You have steam, then you have a turbine, you have generator, and you have switchyard. So on the left, to the end of the left, it's a switchyard. And as you can see, the nuclear part is very small. I mean, the cylinder on the picture is the core. So the core is very much a small unit compared to the whole power plant. And most of the parts of power plants are conventional. There are no difference from a coal or gas or other type of a power plant. So that basically show a nuclear is very compact. That's how we can keep the cost low. And here's another angle to look at the power plant. Again, on the left, you can see a cylinder, a blue cylinder, and that is the core. So that's very small, and the rest of the components are just supporting the operation. And here is the energy flow diagram. Basically shows all the loops, the temperature, the pressure, the flow rate. So basically the pressure is close to atmospheric pressure. The temperature is relatively high. It started with 700, and then on the steam side, it's about 550. And then you have a high pressure, mid pressure, low pressure turbine, which is very typical and standard for the industry. Here is the closer look of the reactor, which is inside the core. Inside the core, in the middle, there's a donut shape, or I don't know how to call that, but that tank is it's a core that where nuclear reaction is happening. At the bottom is what we call drain tanks. So if we want the reaction to stop, let's say if you have a tsunami or earthquake, you want the power plant to stop, then you drain the salt into the drain tank. The salt will just flow into the drain tank without any power, because the gravity, which you cannot defeat it on the earth. And once the salt is drained into the drain tank, because the geometry, the chain reaction will stop, and the shell of the tank, the blue one, they're surrounded by water. Through the natural circulation of water, the residue heat or decay heat will be taken away from the fuel. So everything will be safe. On the left, it's a list of parameters. As you can see, the thermal output for each can is about 557 megawatt. Then on each unit, you have 2 cans in operation at the same time. So it will give you over 1,000 megawatt thermal power, and you can generate 500 megawatt electricity from that thermal power. Okay. So I just want to use several slides to go through the safety features of this particular design, because I know people are very much interested in whether the ThorCon design is safe. First of all, we want to talk about the control, which actually the control of reactivity. So how do we do that? The first, we always prefer to use intrinsic safety features. So we have a negative temperature coefficient of reactivity. So when you have a temperature rise, the reactivity will go down. So typically, when things goes wrong, your temperature will increase. And then in that case, we will have a lower reactivity, and then you generate less nuclear heat. So the temperature will go down. So it's a negative feedback, and to ensure the system is stable. And then if that's not enough, we have shutdown rods, just like any other nuclear power plants. The shutdown rod drop by gravity. So it inserts the neutron poisons into the core, and the reaction will stop. And on top of that, we also have this freeze valve and drain tank. So in the previous slide, I introduced the drain tank. And how do we get the fuel salt into the drain tank? In the normal operation, there's a freeze valve underneath the core. So basically, how the freeze valve works, it has a helium cooling system that freezes the salt. So you form a section of solid salt, so that the salt in the core won't flow into the drain tank. That's in normal operation. But if something goes wrong, the temperature rises, or let's say we found something wrong, and then we cut the helium cooling system, then the salt will melt, right, by the heat. So once the salt melts, the solid section will be gone, and the salt will flow automatically to the drain tank. So into the drain tank, because the geometry, the chain reaction will stop. So we have a multiple ways of control the reactivity of the reactor, and all of them, and none of them requires any power or operator actions. The second point is cool. So how do we cool the nuclear fuel, especially when we want to turn off the reactor? So everybody remembers the Fukushima Daiichi accident. So when you stop the reactor, and you still have to cool the irradiated fuel, right? Either in the core or in the used fuel pump. So if you don't cool that fuel, then the fuel over the time, the temperature will rise, the fuel will melt, it will release radioactive material. That's exactly what happened in Fukushima. And we have a much better way of maintaining the cooling. So as you can see, there's everything, the core, the can, everything is submerged in water. Basically, the bottom half of the power plant is filled with water. So the heat will be transferred from the fuel through the containers to the basement water. It's a natural circulation. We have designed the channels to facilitate the natural circulation to transfer the heat. And then once the heat is in the water will evaporate, and it will take the heat into the atmosphere. So the atmosphere is our ultimate heat sink. So it will never disappear. We can always cool it. And it only depends on how much water we have in the basement. In fact, we have enough water to cool the used fuel for over half a year without any actions, without any external support or electricity. So that is far beyond the current requirement. Typically, the nuclear power plant will be required to cool the fuel for 72 hours and until there's external support. But we can do that over half a year. The third point is contain. So it's all about contain the nuclear material, the radioactive material inside the container. We have multiple barriers to restrict the release of radioactivity. As you can see, we have multiple layers of steel. They're very thick and they are leak tight. And also the molten salt itself is quite stable. It forms the stable compound with elements like cesium, strontium, and they have a higher, they can be dissolved into the molten salt. On top of that, we have all these mechanical barriers. And the last one is a combination of steel and concrete, which is the outer layer of the power plant. It's there to defend the power plant against external impact, such as an aircraft strike. So with all this control, cool, and contain features, we can ensure the safety of the ThorCon design, which of course we're not going to be stopped there. And that's our design. And we're going to ask independent organizations to review it. And in fact, it was requested by the government of Indonesia. So we're working with our partners, both in Europe and also in Indonesia, to form a independent review team to give a thorough review of this design. And after that, we're also going to do a test. You probably heard Bob talked about the precision test platform, which we call PTP. It's going to be a full-scale test platform. A lot of these features, cool and contain, can be tested there. And our activity, our collaboration in ITB is one of the first steps towards that full-scale testing. But why all this matter, right? Why molten salt? Why try so many things, spending so much time to ensure the safety? Why all this matter? Well, it matters because the world needs clean energy. Now, typically the access to energy is at the heart of the development. That's what the World Bank is saying. And at the same time, we want to ensure the damage or irreversible damage to the environment and climate is controlled. So we do not want the energy has a high carbon emission. We want a low emission. We want a zero emission. That's how nuclear can help. So here is a short summary of what world electricity generation from 2010 to 2050. On the left, as you can see, is the prediction of the OECD countries, which basically developed countries. And as you can see, their demand it's quite flat. But as you can, so the bottom light blue ones, they're OECD countries, right? The darker ones on the top, they're non-OECD countries, which basically developing countries. But there's a big gap there. If you look at two lines, so the bottom one is the electricity consumption or generation per capita for developing countries, not non-OECD country. The top ones are OECD countries. So there's big gap there. The gap, in my opinion, indicated the living conditions, the development index. So if the developing countries wants to have the same living conditions for everybody as the developed countries, the energy per capita energy consumption needs to increase. But of course, the energy needs to be clean energy. And on the left, it's a very conservative estimate. So as you can see, even though the developing countries their consumption are increasing, but their per capita consumption remains low, and the gap between the developing world and developed world maintains the same gap. The increase is mainly due to the increase of population. So that means the living conditions won't be improved. But if you look at the right, it's a more bold estimate. Let's say if developing countries want to have the same living conditions as the developed countries, the energy demand will increase tremendously. So why it has anything to do with Indonesia? Well, Indonesia is the world's fourth most populous country with 270 million people. But here people only consumes 1/6 per capita electricity of Europe, especially in the rural areas, the consumption will be even lower. So in ThorCon Indonesians' mind, the idea of development needs tremendous amount of clean energy, and we think our technology can facilitate that development in Indonesia. So here is a short summary of the short prediction of the future. Now, today, Indonesia generates 0.28 trillion kilowatt electricity per year, which is only 1/2 of France. Now, if we follow the historical trend, Indonesia needs to add another 1/2 of France electricity generation by 2050. So just follow the historical trend. But if we follow the historical trend, the per capita consumption will be similar because the increase is really due to the population increase. So let's say if we want to reach a non-OECD average. So the fact is the Indonesia's per capita consumption is lower than the average of the developing country. Let's say if we want to reach that non-OECD average, then Indonesia needs to add 1.25 francs, right? If we're more ambitious, we're bold, we want to reach OECD average, which is not very high. I mean, OECD, you have United States and Canada on the very high end. But in OECD, you also have a new OECD country like Mexico, I don't know if Malaysia is also part of it. No, not. But Mexico is. So in that case, the average is not that very high. And just reach the OECD average, becoming a developed country, Indonesia needs to add 5 francs, right? So currently, the Indonesian government predicts that the country needs to add 350 gigawatt capacity by 2050. So no matter how you predict the future, the most conservative one, the most optimistic one, the answer is the same. Indonesia needs a lot of electricity. And so on this slides, I just want to ask one question. So with all this demand from Indonesia, can nuclear help? Well, the answer is not with the traditional nuclear, because the pace of the construction of traditional nuclear is too slow. The cost is too high. And currently, the Indonesian government predict that in the future, there will be 15% of nuclear, which is about 90 gigawatt. And how can Indonesia get those 90 gigawatt? Not possible with the traditional nuclear. If you look at the development around the world, in the United States, in Finland, in France, it's not possible to get 90 gigawatt. It's about 100 new nuclear power plant in Indonesia. Imagine that by, I don't know, 2050, which is only 30 years from now, building 100 traditional nuclear power plant in Indonesia is almost impossible. If you ask anybody, nobody would tell you that's possible. So what we need in this country is to deploy a massive nuclear power plant fleet rapidly, which is not possible by traditional nuclear, but we can do it with ThorCon Indonesia. So why? Why it's not possible for traditional nuclear, but we can do it in Indonesia with ThorCon? Okay, so the fundamental difference is that we're not building the nuclear power plant the traditional way. We're building them as a fleet, right? The country needs a fleet. We're building a fleet for the country. And so if you imagine this, the ultra large crude carriers in the world, many of them were architected and managed by the co-founders of ThorCon. So ThorCon came with a background of building large ships, and our power plant is not designed as a building, it's designed as a ship. So we can take advantage of the existing shipbuilding industry to quickly deploy the technology. The size of the ThorCon power plant is similar to a large ship. If you look at around the world, so many ships on the ocean, they're everywhere. They're a large quantity. Maybe each ship only takes a year to be finished. So it is very possible, it is very feasible to build a large nuclear power plant fleet as a ship fleet. So what is the benefit of building it as a ship? First of all, it's low cost, and second is rapid construction. So we're not building this on the remote site. We're building it in the shipyard on the production line. So we're building it as a car, as a ship. The high precision steel fabrication makes ship under $1,000 per ton. And a shipyard can build, so the one shown on the picture on the right, it's a shipyard in South Korea. As you can see, that's Hyundai. And the shipyard can build, this particular one can build 20 gigawatt ThorCon power plant each year. So if you need 90 gigawatt, you only need 5 of those shipyards, and you can find that in the world. It's not only fast, it's also cheaper. And so ThorCon has several features that makes this cheaper. We're using low enriched uranium, fluoride salt fuel, graphite moderator, thermal spectrum, replaceable core. And all this are a modular design. So everything is replaceable. Everything is building on the production line and assembled in the shipyard. So based on our calculation, the cost for 1 gigawatt is about $1.2 billion. and you can convert that to Indonesia ruby. It's about 17 trillion. That's today's price, and the electricity cost can be as low as 3 cents per kilowatt hour, but you have to add other costs like licensing, like land and operating and everything else. But still, it's comparable with coal. So our goal is always keeping our costs at the same level as coal. So when we deploy nuclear power to replace coal, it won't increase people's electricity bill. So how does this work? We're gonna build the power plant in the shipyard. On the left, it's a picture of the shipyard. And then once it's built, we're gonna barge it to the site. Basically, we're gonna tow it to the site to one barge per 500 megawatts. So the one I just shown on the previous slide, it's one ship that we can tow it to the site. And then once it reaches the site, as you can see on the right, then the power plant or the ship will be ballasted or tethered to the seabed. And so there's only minimal on-site construction. Almost everything is done in the shipyard, in the workshop. And then when we need to refuel, we'll have the can ship to ship the fresh fuel to the power plant to refuel. And when the power plant reaches a lifetime, say 80 years, and at that time, we would just barge away from the site for decommissioning. So very clean process for this all construction and decommissioning. So where is the first power plant site? It's gonna be in one of the islands in the Bangkok province. And the PLN engineering has started the site study in September this year. In fact, they have just finished the study and writing the feasibility study report. And as I said, we want to make sure everything is working, everything's safe. So we have the plan to have the full-scale test platform, which we call PTP. As you can see on the slide, it's going to be full size. Everything will be tested, and we're also going to do some intrusive and destructive tests. So make sure everything is safe, and we can also accumulate operating and maintenance experience. So that's very valuable for the first reactor. So when we start our first reactor in Bangkok province, we already get experience. We already prove our technology on the test bed. And another important question is, okay, let's say we get the fleet, but where can we get those navigators and deckhands? So how do we have our workforce, right? Because we're saying we need 100 nuclear power plants in Indonesia. So who are the people who can maintain and operate it? It's a monument effort to train that workforce. Yes, that's true. That's true for the traditional nuclear because their operator needs to take immediate action when anything goes wrong. So if they didn't take the right action, a tragedy will happen, as you see in the past, what happened to 3 Mile Island, Chernobyl, and Fukushima. There's always human errors involved. So we think we have our design addressed this issue in the design. What we have done is that we make sure that every safety system will work by themselves. We do not require any operator actions to make sure to ensure the safety of the power plants. So the safety is either ensured by passive features, intrinsic safety features, or it's done by automation. So our operator is just there to monitor the status and to generate the electricity for the utility companies. They do not have the responsibility, or they're not required to ensure the safety. So that's a big philosophy change. So by having that, we can significantly simplify the workforce training program, because our safety is not rely on those operators. So we believe it's a good way of deploying a large number of nuclear power plants in the country new to nuclear. So here's a further explanation on that. Now, in the air plant industry, you have two major companies. The Airbus, in their design, they always places the autopilot and hard limitation at the center of the design. So that means they always prefer the autopilot, the computer, than the human pilot. And the Boeing is the other way around. So Boeing gives the pilots more authority. So they can always override the autopilot. So they're at the center of the safety. So ThorCon chose the Airbus approach. So in the ThorCon plants, it operated in a highly automated environment. So human operators have much less responsibilities comparing to the traditional nuclear power plants. And the plant safety system always override human actions. So in fact, the human operators cannot do anything to deviate the nuclear power plant from a safe state. So we basically eliminate many of the human errors in the design. So we address the human error issue by engineered features rather than through trainings, through the controls of procedures. So in summary, the ThorCon plants will operate safely in the countries that without seasoned pilots. We think it's extremely important for the for the massive deployment in the country that's new to nuclear. So in summary, we have a molten salt reactor technology that can provide the world with low cost dispatchable power that's clean and safe. And we have a vibrant team in Jakarta and team members around the world working on building the first nuclear power plant in Indonesia. And Indonesia has an ambition for cleaner, more prosperous future. We can help. Thank you all very much.
Thank you very much, Professor Kun Chen, for very nice explanation about the MSR. Okay, so we'll move to the question and answer session. But beforehand, please let me greet our Vice Rector of the Research and Innovation, Professor Igdo Wenten. Selamat pagi, Pak. Okay, now we are going to the question and answer session. Okay, so if you have any question, you can ask by typing your question in the chat box. Right now we will have, okay, I think we have several questions here. Let me start from the beginning. Okay, the first one from Shahrir Isdiawan. Good morning, I'm Shahrir from Chemical Engineering ITB, and my current experience in, okay, sorry. Okay. So. Okay. There.
To a certain temperature. So it's above the melting point. And so that's one measure. And the other is the molten salt itself actually has a relatively higher heat capacity. So it's not that easy to freeze. So combine both of the features, we don't expect the clogging will happen. But again, as I said, we will have the test bed. And so our current thinking is based on the test that has been done by people in the past. But we're going to do a larger test to make sure everything will work.
Okay, thank you very much. So let's move to the second question from Joko. Question, how to prove the optimality of fuel composition from neutronic safety and security aspect to produce heat and then electricity? The second, in what way ThorCon will find the composition? Maybe all the composition, maybe the salts and also the structural material. How much is the electric cost can be sold to PLN or Indonesian government, and how to find the licenses from regulatory body? Thank you. Maybe that's.
Okay, so the first two questions
maybe next month. So and then the student from ITB we will also visit the US lab to share experience. So we have a good team, a good international team working on that. So I have full confidence that this will be worked out. So the third question. So how much is the disconnect? Oh, disconnect. There's a disconnection. Oh, it's a I'm working with the Fleabag and cleanup for the test. Fleabag. He is not professor yet, but yeah, he works for material corrosion.
This.
Yeah, applied, yeah. Okay. Sweet. Oh, wait. Oh, wait. Okay. Wait a second. Okay, let's start. Okay, let's continue our Q&A session. So yeah, you have answered question number 2, and it's interesting because you talk about he asked about the neutronic safety and security, and usually the material is always the limitation factors, right? In as a materialist, is I think it's almost for every system, any system that okay, you can design very sophisticated anything, cars or everything, but somehow the materials will be the limiting factors. And as far as I know, regarding the molten salt, whether it's a fly or fly neck or other things, the corrosion is one of the main factors to ensure the safety, especially for the structural materials. And I was work for the LFR, lead bismuth fast reactor, and we do not like to have structural materials that the chemical content is containing nickel, much nickel. In opposite with the MSR, how did you deal with ensuring that technology can cope the corrosion aspect in this case?
Okay, so the question about how do we address the corrosion issue? The corrosion issue has two sides. So because we're worrying about the structural material can be corroded by the salt. So you have to work and structural material. On the structural material side, we are choosing stainless steel as a material because it's low cost, its manufacturing techniques are established and the regulators are familiar with. It's cold material. So in your
we're working in the laboratory to test our ideas. And I mean, you ask another excellent question, because the experiment will also, the cleaning of the soil will also be done in IPP. Yes. So I'm sure you will have a lot of discussion with your colleagues in IPP.
Recording in progress.
If you are interested, and then so if you get a clean soil, good structural material, then you still want to make sure you control the erosion. So one way you can do it, you can dynamically control it by using electrochemical methods. So you can check the potential online, and then you can adjust the redox state, because once you have ingredient, things will become more complicated. You need that online redox. And then 2 phase is better. So we replace the core every 4 years.
Recording in progress.
The operating temperature? Yeah, I mean, your standard for melting the
the cooling, then we go back to 700.
Ada restart ininya, sistem internetnya di restart. Oh ya.
So we
Okay, so
start.
Yeah, we'll continue. Okay, yeah, thank you very much for your explanation about that. Now we move to the next question. Good morning, I'm Christopher, a physics undergrad in ITB, one of the. Okay, oh, okay. Yeah, okay. From Joko, yeah. How much is the electric cost can be sold to PLN?
Well,
in terms of ThorCon?
let me do this. Let me jump to question 4 first. So obviously the regulatory body will be Bapeten in Indonesia, and we just had a meeting workshop with Bapeten last week. There's lots of things under discussion, but I think both sides are optimistic about the moving forward with the licensing process. And going back to the third question, I'd like to give this question to Bob about the cost.
The cost we are discussing with PLN right now at around 6 cents per kilowatt.
6 cents. Okay. Can you hear? Please. Okay, please, Mr. Bob.
So currently we've been discussing with PLN for the past 3 years. You know, the price sold to PLN, we are discussing at around 6 cents. 6 cents per kilowatt hour. That is way below the national BPP, the electricity production cost, which is at 7.66. So we are selling under the national BPP. So in hope, so if we have a fleet, then it would lower the national BPP. So if it is lower the national BPP, the impact would be the national TDL, the electricity paid for the customer, which eventually will be lower. So if we have this fleet, the one that Kun are seeing, the potentiality of we are selling at 6 cents, replacing all the coal, that it would eventually lower the price of the electricity to the customers, which never happen because the price of electricity to the sold to customer every year and year, as we all know, is always increasing. So there is that possibility if ThorCon power plant is put as a fleet, very large quantity. So
it's after calculating, including all the expenses,
including
the experiments,
including everything. So we are, so that 6 cents we are selling to PLN around 6 cents. So we're still negotiating at like 6.5 or 6.3, 6.7. So, but we have all agreed that around 6 cents. And that's including the commissioning, the waste, the whole thing. So the government do not need to pay anymore. I mean, that's the whole price. Only and including all the development. So yeah, that's it.
Okay.
Oh yeah, also that we have studied, the Ministry of Energy has verified this number. They have verified. So they have verified the cost of the production, which Kun has already mentioned, slightly under 3 cents. They have verified this number. And so they have also calculated, verified that we can sell around 6 cents. We can sell. So in fact, I think the finding was they said we can sell under 7 cents. So around 6 cents. So it is a number that has been verified. Of course, the Minister of Energy cannot dictate because how much we sell is basically a B2B negotiation with PLN.
But yeah, I think there will be costs that maybe, as mentioned by Professor Kun Chen, that you will have the 4 years, maybe 4 years or several years for it's a test bed or
yes,
like full scale.
We're going to build a full scale test bed, but the cost of that test bed is included in the development cost.
Yeah, it's already included in the $1.2 billion.
But yeah, we will see if there's any issue after then. Yeah.
Yeah.
And then
in fact, during the analysis that Minister of Energy that did, right?
Yeah.
They did the analysis in 2019-20. They did analysis of, I think it was like 6 year or 5 weeks overrun, meaning overrun that the time we're planning for this much, and so they add another 6 years, and they add another overrun of budget, several hundred millions of dollars. So we still can meet that price range. So they did several scenario, with the interest rates and with the overrun of timeline of the schedules and also overrun of budgets, and to see whether we can still meet that price range that we are projected to sell to PLN, and it still fits in that price range. Yeah, even with overrun of time, overrun of budgets, everything. So we are in a good position. That's why that's one of the reasons that the government are giving a recommendation, to prepare for all these studies.
Okay, let's move on to the third question. I think I have read that. Could you please?
Yes. Okay, so
I think he's asking about the thermal hydraulic something during the
Okay, again, thank you for the question. I think this question about volcano it's an excellent question. So first of all, our system, we did the analysis of the natural circulation, and we used a very conservative numbers for the air temperature. I think it's about 40 degree, already consider the tropical weather we have here. And about the volcano, we identify this as a unique risk or hazards in Indonesia. And first of all, we don't want it to be too close to the volcanoes. I mean, I consider the lava will be more dangerous than others. So we're going to keep away from the active volcanoes. Now, eruption, yes. So it's going to change your the local climate. So we're working with UGM to evaluate the volcano hazards. They're doing the analysis. They're gonna taking our design and with the volcano situation in Indonesia and use and consider volcano as external hazards to the power plant and evaluate the safety. So it's being considered, but it's good that Christopher thought about this. I think it's an excellent question from a student.
Yeah. Okay. Okay. Thank you very much. Okay. Any other direct question? Okay, please.
Okay. Thank you. Thank you, Dr. Kun. Very nice presentation. I just curious. Maybe my question is.
Sorry.
My name is Imam. I'm from the Department of Metallurgical Engineering, and we quite often meet with Professor Kun. And thank you for nice presentation, Professor Kun. My question is maybe related with the first question from Sahrir Isdiawan. So far, how you predict the high temperature property of the salt? Because before you design, you have to know like the viscosity, and then the solidification property is like what the compound you will have, because it is affect how the fluid moving.
Yeah.
And because if we based on the experimental results, currently it is very limited data, I think, especially because it is difficult to conduct the experiment. So how you predict that such kind of property at high temperature? Okay, thank you.
We are going to measure it in the laboratory. We have 2 laboratories in the United States. We have a contract with them. They're going to measure it. And we're also hoping that ITB will be the part of the team and do the measurements.
Yes,
so
sure.
Then in that case, we will have 3 independent labs doing the measurements. So that will give us the confidence that the result will be reliable and accurate.
Okay, thank you. Yes, I hope so. In here we can do experimental. Also, we plan to do the modeling, using Kalpak modeling to predict the thermodynamic properties of the.
Yes. So modeling is definitely one of the methods that we're using. Actually, before we do the experiments, we always predict, what value we can get. So we did the literature study, basically study the data the people have obtained in the past. And then we also did a simulation. So it's a combination of a simulation and testing, but eventually the result of the simulation will have to be validated by tests.
Okay, so you mean the property, the chemical property, and
yes,
things,
that can also be calculated.
Numerically. You mean the information of the operating properties during the operating, or you would like to test the property above or in severe accident condition?
We will have a set of properties. For example, heat. It's going to change under different temperatures. So we will measure the value for a range of temperature. So going all the way up to the accidental conditions. So as higher as we can go, and low also as low as we can go. So we have a range of temperature covered. So that is in the plan, and the labs are doing that.
Yeah, because as you mentioned that this Msr technology has been has been developed for a very long time, in 1970, about 1970. So
So, but it's a 1/4 of the full scale. Right. But the fundamental thermophysical properties are the same. And also, but the reason we also want to remeasure it because today we have more advanced equipment compared to fixes. So even though their values were good for their operation, but today we have higher standards. So we want to remeasure it using the most advanced equipment to get more accurate standards.
Recording in progress.
Or several minutes. Thank you.
I think there's another question. Yeah.
Okay, is there any other question? Or direct question, maybe?
There's a question there.
Okay, okay. From Satyawan Anugrah Haryanto, yeah. How the nuclear fuel loading, unloading path mechanism, okay. Maybe he needs in detail about how to load the fuel and unloading and how to make sure the amount of the nuclear fuel in and out. Okay, so it's basically about that.
Okay,
fuel.
so for the first question, the fuel, let's use the fresh fuel as example. The fresh fuel will be contained in a fresh fuel tank, and then it will be shipped by the can ship to the power plant, and the container will be transport from the can ship to the power plant. It will be lifted and be lowered to the power plant. Once it's in place, we will connect the pipes and valves, and then we will use let's say argon gas to pressurize the fuel and push it, or you can say pump it or push it into the core. So it's a very technology. It's a liquid transport, and so how do we make sure that the amount of the nuclear fuel in and out is right? So it's like a transport water. How do you make sure the right amount of water is in the container? It's the same technology. You use a lever indicator. You use a lever. You know how much salt, which is in liquid form, right? You know how much salt in there, and there's also you can using a flow meter.
How it counts the amount of material. Basically, you stop and then you pump it out, but do not use this valve, right? No. So next question is there okay.
The traditional nuclear, as I said, we're doing online refueling. So what they're doing in light water reactor is every like 18 months or 12 months, you turn off the reactor, you open the containment, open the pressure vessel, you unload the fuel, and you load the fuel at once, right? All the fuel for the next 18 months will be loaded at the same time. Well, we're not doing that. We fill the fresh fuel into a tank, and during the operation, we fill the core little by little. Just fill enough fuel, maybe for the next week, for the next 2 weeks. So it's a continuous refueling.
Okay, let's have another question. I hear that there are only 2 or 3 MSR in the world. Now what's happening? And maybe MSR? Okay. She mentioned small modular reactor. There hasn't been It's going to Russia. Is Msr. Okay, maybe. Can you get the question, because she was asking about MSR, and then
I can't really understand the questions.
Okay. Maybe the question, maybe I can assume that there are very limited experience regarding the MSR reactors, and because she mentioned about the small modular reactors, and
okay, so maybe she's worried about the over budgeting, right?
Yeah.
So when we go to the government, we say it's gonna cost 1.2 billion, but once the construction started, we say, oh, we need $2 billion, right? That's what you see in many other countries. But our business model is different from those companies. So typically, a company will go to the country saying, I'm selling you the technology. You take the financial responsibility, right? I'm just charging you for the design, right? Your local companies, utilities, they will pay for the construction. If the construction cost is higher than originally planned, the utility company, in many cases, the government will have to absorb the loss, right? It's called over budget, everything goes slow, and eventually, sometimes the government will have to eat the loss. Sometimes the government get angry and they say, okay, we're gonna cancel this, stop doing that. So we're not taking that approach. As you see, what Bob said, we're selling the electricity to PLN. So at a certain fixed price, if it's go higher or if we cannot build it, then PLN won't pay anything, right? There's no risk to the Indonesian government. There's no risk for PLN. There's no risk for any customers. So we are financing the nuclear power plant. So we're controlling the budget. So if there's a if we run over the budget, the loss will be on ThorCon, of nobody else.
Okay. Yeah. Is there any question from the chat? If no, I have several questions, because I'm a materialist, and as far as I know, that the salt will be tested in ITB. Yeah. And as far as my concern, I also have an experience working with the FLIBE and FLINAC for the fusion. And right now, FLINAC for fusion reactor, but the fusion reactors, and fortunately, it can be used in the MSR also. And I also work as my PhD work with lead bismuth, and lead bismuth is the opposite. We would like to have chromium in the stainless steel, as you mentioned that you will use stainless steel, and in stainless steel you have chromium and nickel, much of them. But in LFR, in lead bismuth, chromium can be the protective oxide layer. Yeah, because we control the oxidation. But somehow in the MSR, it's the opposite, that you don't like to have the chromium, but stainless steel using chromium as it's one of the, not major, but one of its composition. So I'm still curious about how did you deal with the material issue, for example, especially when the condition, for example, at high temperatures. Yeah, high temperatures, we have a lot of reference that high temperature, of course, it's increase the corrosion rate. Maybe the corrosion not really thick, but the effect in mechanical properties might be severe. Yeah, I'm still curious about that, and which laboratory will be conducted for that test.
Let me try to answer this question. So the let's say if we choose the stainless steel as a structural material, and then we have to worry about the salt. We have to make sure we control the corrosion on the salt side. So first step is to make sure the salt is clean. So we know that when we have a excessive oxygen or sulfur in the salt, it will corrode more. So we want to clean the salt, which is also part of the ITB's activity here. And the second one, we will do the redox control. So we control the reducing and oxidation status of the salt. It's a dynamic control. We use the electrochemical mechanism and do that. But even that, we know because the chromium is in the stainless steel, so there will be corrosion. So we replace the equipment including the core, everything that in touch with the fuel salt. Basically the primary loop. Yeah, basically the whole loop will be replaced every 4 years.
Okay.
So
it's interesting. Even though we can control the impurities, somehow the nature of diffusion of chromium inside the molten salt environment is still there.
Yes.
Is still there, and also one method is that we control the saturation of the chromium inside the in case of lead bismuth. But as you mentioned that this will be 4 times bigger than the previous MSRE.
Yes.
So I'm curious whether you can get the saturation condition for that or not. But it's interesting. I think it's still in research topic and fruitful discussion.
Yes, yes.
I think that.
Yes, I think the corrosion study will not end. And I mean, even after the operation starts,
Exactly.
you will continue doing the monitoring, you continue to do the improvement.
Yeah, as one of MIT professor said in our class, that even though you bring your new materials, your new alloys, that new alloys will bring its own problem for the. Yes. Yes, please.
True that, over the years that this issue about corrosion has always crept up in all this discussion, right? But again, what people realize to understand is that it's all this material thing on the nuclear power plant, especially in corrosion, like in the lead bismuth, could conceive as problems because the difference with ThorCon, we don't see corrosion as a much of an issue because basically the main difference is that in other type of reactor, the reactor itself need to be installed, like 40 years, 60 years, right? So then it become an issue of the corrosion creeping up on the materials, right? And on the ThorCon plan, that as Dr. Kun has said, that we replace the can every 4 years. So even though there is some creep damage, the chromium is depleting, but it's like micro, it's like, it's kind of not affecting at all. In fact, during the Msre operation, the corrosion is because happening when, if I'm not mistaken, is when they decommission the reactor Msre, that they see there is some creep damage due to the corrosion, but it was not impacted towards the operation of the reactor itself. They operated like 5 years. So because we have very thick steel and we change the reactor, the can every 4 years, so whatever the creep damage to the steels would not affect that much to the operation of the reactor or even the safety aspect. Whereas like in the lead bismuth, because you design the reactor to run for 40 years, right? You cannot replace the reactor, right? Like 40 years or 80 years, then the corrosion issue become a major safety issue. So I think that's the difference. So we take a practical approach because our reactor are very, very cheap and other reactor are very, very expensive. So rather than, thinking about very expensive material, rather very exotic material, we just remove it. So we take the practical issue. So I think, just to add more perspective on the discussion.
Yeah, thank you very much. And I think the key point is that you remove the can. Okay, they can, because it's not just creep, but intergranular corrosion also taking into account. Okay, thank you very much for fruitful discussion and for having you here, Professor Kun Chen. It is very nice to have you next time to have another discussion for this. And I think we have to conclude our meeting today, but for the closing remarks, I would like to have the chairman of LPPM ITB, Pak Dr. Yuli Setio Indarto, for the closing remarks. Please, Pak Yuli.
Yeah, thank you, Pak Asril, Professor Kun Chen, our keynote speaker. Thank you very much for your important presentation. Clear, I think, and clear discussion also with the audience. Thank you, Pak Wendem, that already joined. And then thank you, Pak Wahyu Sri Kutomo, the Dean of Faculty of Mathematics and Natural Sciences at ITB. Thank you, Pak Bob, CEO of PT ThorCon Power Indonesia and College. Of course, I'm following this discussion fully from the beginning until now, and I would like to thank Professor Kun Chen, who has delivered a talk in this important event. I hope this event give a new knowledge for our college in ITB, and maybe also for other colleges from other universities and entities. ITB and PT ThorCon Power Indonesia will commence cooperation for this nuclear fuel, mainly for the molten salt reactor that may support fundamental research in the field of chemistry, chemical engineering, and metallurgy. I hope this collaboration will give birth to sustainable research and innovation ecosystem, as well as for ITB and Indonesia. Developing research culture based on scientific merit is the key to bring innovation for solving our nation problem. ITB is persistent to bring our program towards the creation of sustainable research culture in Indonesia. We are eager to collaborate with worldwide professors. Today we have Professor Kun Chen. And then we look forward to collaborating in development of the nuclear science and technology. Particularly today, we talk about the molten salt reactor technology. Eventually, the organization of this focus group discussion hopefully will broaden up our knowledge. And once again, the technology innovation based on scientific merit is the key factor to finding success for building up our nation's own technology. Thank you for all of your participation. Thank you once again, Professor Kun Chen, Pak Bob, and the Dean, and all of the audience, and of course, for the committee organizing this event. And I'm sorry for the internet connection problem for several times on and off, because of connection condition in our building. See you in our next FGD event of LPPM ITB. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Yuli. Great. Once again, thank you, everyone. We appreciate you being here. And thanks again for joining us today. And we will see you next time. Thank you, Professor. Thank you. Assalamualaikum warahmatullahi wabarakatuh.